Welcome back, folks. So hopefully you watched the previous video on how, or the previous two videos where we worked out a specific example of evaluating a geometric series, pulling out that funky algebra trick, and then hopefully you watched the follow-up video where Eddie Wu explained how you can how you can derive that generic formula, generally. Okay, and so here's what that formula is. Again, if I want to evaluate the nth partial sum of a geometric series, I take a times 1 minus r to the n over 1 minus r. Again, be careful about what these things actually stand for, and I think it just helps to kind of understand that. So a, remember that a is really just the first term that you're adding. It's not necessarily a1 because you might be concerned about, maybe from a2 to a12 or something. But it's just the first one you care about. And the reason that it's okay to do this is because no matter where you have wherever you start your series from, like let's pretend you have the series 2 plus 6 plus, so I'm going times 3, 18 plus 54, and so on. I might start here, and then in that case that would be your A, but there's no reason you couldn't just, maybe I want to start at 18 for whatever reason. And in that case, that will be your A value, okay? So that's what A is. It's really just the first term that you're using. And then n is, well, it's the number of terms that you're actually adding, the number of terms you're adding. Again, the reason that this is helpful is because if you designate whatever you're starting at as the first term, then the nth term is the number of terms you're starting at, or the number of terms you're adding up. And likewise, r is, of course, our common ratio. So what I want to do in this video is actually just work an example of where we can use this formula. Okay, so here's an example, and I actually used this problem on a test, or at least the setup for it. I didn't actually ask them to evaluate it. So let's pretend that Lexian here drops a bouncy ball from 50 feet high. Excuse me. And if the bouncy ball, let's pretend that there's no air resistance and doesn't lose any energy to the ground, etc. Pretend that the ball always returns to 2/3 of its original height. The question is, what is the total distance that the ball travels as we go up to the 11th bounce, but not including the 11th bounce? So I've drawn the visual here of what happens. So Lexian's standing on, the roof of this building or whatever. She drops it from 50 feet here, so this is 50 feet right there. And then after it bounces once, it'll return up to, 2/3 of 50 feet. So that's 2/3 there. And once it'll come back to the ground. And then when it bounces up that second time, it's going to go 2/3 of that. So I will multiply by 2/3 again. Okay. So if I want to evaluate the total distance, I could rewrite it like so, or represent it like this. So it's going to travel that 50 feet initially, that initial drop. So that we'll say it is the initial drop. Initial drop. And then what happens? Well, after the first bounce, it'll bounce up this much, 50 times 2/3. But I need to double it. Why? Well, that's because on the way up, it goes 50 times 2/3 feet. But it also has to fall back down. Don't forget that part, right? So again, this is the return height. And then times 2, it has to fall back down. It has to fall back down. So again, the initial drop, well, it doesn't go up 50 feet ever because we're just assuming we're not measuring until she drops it. But everything after that, after all the bounces, it bounces up but also falls back down to earth. The next bounce, so again, this would be like bounce 0. So that would be bounce 1. On bounce 2, again, it would go, well, whatever that initial height was, that bounce height that it reached after the first bounce, on the second bounce is going to go 2/3 of that. So 2/3 of 50 times 2/3 would be 50 times 2/3 squared. But we need to double that again. If we follow this through again, what bounces do we want to measure? Well, we want to measure bounce 1, 2, 3, all the way up through 10, again, going up and then down, but not 11. So we're going to stop this. Oops. At bounce 10 here. Oops, sorry, that's a C. Bounce 10, which is going to be 2 times 50 times 2/3 to the 10th. Okay. So again, that's just the setup for this problem. Okay. If I want to actually set up sigma notation for this, then I could say it's 50 plus, so this is a kind of neat trick about sigma notation evaluating sums, is that sometimes I can't apply the pattern to the entire expression that I'm looking at. But that's okay if I leave out one or two terms, because again, you're just adding things. So whatever this number is at the end right here, I'll just tack on plus 50 to count for the initial drop height. So in this one over here, we're going to start off from, since we're starting off at bounce number 1, I think it makes sense to have our counter start at 1. Up to bounce number 10. And it's going to be, well, let's see what always stays the same in this series here. Well, there's always a 2. There's always a 50. And the only thing that changes is how many 2/3 we're multiplying by. In bounce number 1, there is 1 factor of 2/3. In bounce number 2, there's 2. In bounce number 10, there are 10. So it seems that whatever term you're at, that's the number of 2/3 you're multiplying by. And so I think this is going to be our expression that we're actually evaluating. Alrighty, so now we can actually apply our formula right here. So I'm going to just repeat that. So Sn is going to be equal to, again, the first term. Don't worry too much about the notation. Your text might be different notation. It's whatever the first term is times 1 minus our common ratio to the n, where n is the number of terms, over 1 minus r. So let's just point out our different terms here, or different values. A is our first term. So the first term that we actually care about is, well, that's going to correspond to when I plug in n equals 1. So let's evaluate 2 times 50 times 2/3. I'm going to leave this all as a fraction and then throw it into my calculator at the very end here. But this is going to be to the first power. So this is going to be, by the way, 2 times 50 is just 100, so we could just drop this in as 100. 2 times 50 is 100, so times 2/3 is, 200 over 3. Our common ratio, as you can see, going from one term to the next, is just times 2/3, so our common ratio is going to be 2/3. And our n is, of course, again, the last term, the one that we care about, is 10 here. Okay. So now we can just plug these in and actually get a final answer here. So our total distance, and I'll just call that d. Sorry, I'll put that over here. Let's drag this around here. Sorry about that. Our total distance is really 50 plus S10 here. So that's going to be 50 plus, so let's see, 200 over 3 times 1 minus 2/3 to the 10th power, all over 1 minus 2/3. Looks kind of messy, and yeah, it kind of is, but this often gets cleaned up pretty nicely because we can do this. So let's see, 50, sorry, not 550. Let's see, 1 minus 2/3 is really, is just 1/3. And I can simplify this, multiply top and bottom by 3. Okay? Or divide top and bottom by 1/3, if you will. Same idea here. So this will end up just being 200 times 1 minus 2/3 to the 10th power. At this point, I'm just going to utilize my calculator. So I have 50 plus 200 times 1 minus 2/3 raised to the 10th power. Be careful of your parentheses and your order of operations and all that. My final answer is about 246.53 feet. Okay, so that's how you can utilize this formula to figure out, the total sum of a geometric series, or sorry, a partial sum of a geometric series. I don't want to say total sum because that would imply like you go on forever, and we'll actually talk about that later. But there's no reason you should particularly believe me, because this is actually small enough where we could do it by hand. So, or one at a time. So why don't you stand by and let me pull up the calculations if you were to do it just kind of one at a time. Alrighty, so what I have done here is I've written out all the bounces. So let's say on bounce 0, which is the initial drop, it drops 50 feet. On the second one, it goes 2/3, and you can see that kind of in the formula here, 2/3 of wherever it came from, so that's B2 times 2/3, times 2, because again, it bounces up and then comes back down. And then likewise, this one is the previous one, times 2/3, times 2/3, times 2/3, and so on all the way down. So on the 10th bounce, it's not going very far. On the 10th bounce, it only goes up, about 0.87 feet, and then comes back down. So if I add all this up, which is what this says, sum of B2 to B12, I just added all these up, and I get, again, 246.53 feet. Alrighty? So thanks for watching. Hopefully you're a little bit more comfortable using that formula if you were having any trouble with it previously. Ready? Thanks for watching, and I'll catch you in the next one.